All right. Let's start chapter 5. We're going to start with some linear differential equations. We're going to start with an intro. I'm not going to write all of these out again. I'm just going to walk you through it, and if you want to write them, you go right ahead. An nth order linear differential equation is defined as a naught of x. So this is the coefficient on y, the nth derivative of y, right? But it can be a function of x. It doesn't need to be a constant, right? So that's just the coefficient on. And remember, when there's parentheses, that means it's the nth derivative. It's not to the power of n, right? And so you got another coefficient that it could be a function of x times y to the n minus 1th derivative, all the way through to the first derivative on y, and then times y equals big F of x, where each of these coefficients, a naught, a1, all of these guys, big F is a function. So all of the a's are functions defined on some interval I. The big F is some function defined on some interval I, and so is y. All of these y's are some function defined on some interval. A naught can't be 0 because otherwise it wouldn't be an nth order. Remember, the nth order is going to be the highest order of your differential equation. So if it's like the third derivative y with 3 slashes, then it would be a third order, right? But if a naught is 0, then you wouldn't have this term. So that's the only reason why it says that. We call the linear transformation L from Fn to F, defined by L is a naught times big D to the nth power plus a1, all of that guy. That's called an nth order linear differential operator. And the nth order linear differential equation can be written Ly equals F. We saw this last chapter also. Yeah. If F equals 0, so this whole equation set equal to 0, then we say the differential equation Ly equals 0 is a homogeneous linear differential equation. Remember, homogeneous means equal to 0. And then if it's not equal to 0, if f of x is not 0, then we call it non-homogeneous, and you'll just have Ly equals F. Note that the set of solutions to the homogeneous linear differential equation, Ly equals 0, it's a vector space. The set of solutions to this equation is a vector space. Specifically, it's the kernel of L, which is a subspace of the domain space Fn. So it is the kernel, and it is a vector space, the set of solutions to this equation. If a naught, a1 through an are continuous functions defined on interval I, and of course the first guy can't equal 0 for all x in this interval, then the kernel of L has dimension n, right? So n is that corresponds to the powers on L also. Now, the general homogeneous solution to, oh, did I skip this? No, I said it. Okay. Then the kernel of L, it has dimension n. So kernel of L is a vector space. It will have dimension n as long as, of course, a naught is not 0. The general homogeneous solution, y little sub h, to represent the homogeneous solution. So when this guy is equal to 0, it's equal to a linear combination, right? C1 times y1, C2 times y2, all of that, that's a linear combination of each of these y's, where y1, y2, and through yn are n independent homogeneous solutions to Ly equals 0. So because they're independent and they span, right? Spanning means that you can make a linear combination of them. So because of those two guys, they're independent and they span it, then they actually form a basis for the kernel L. Okay. Those are all the theorems we need and the definitions. So let's do an example. Given the differential equation, the second derivative of y plus y equals 0, so that's a differential equation. We're going to verify that f1 of x is cosine and f2 of x equals sine These are both independent solutions to this differential equation. Keep in mind f of x is y, so yeah. All right, so let's do that. So go through example 1. So given the differential equation, y double prime plus y equals 0, first thing we're going to do is verify that cosine of x and sine of x are independent solutions to this differential equation. All right, so what we're going to do first, let's start by verifying f1. So if f1 of x, that's cosine of x. What's the, and I'm going to plug in f of x into y, but I need the second derivative to plug it into this equation to check it. So take the first derivative. Derivative of cosine is negative sine. Take the second derivative. Derivative of negative sine would be negative cosine. Now, so we're going to plug that in to the differential equation and see, is it equal to 0? Well, second derivative is negative cosine of x. First derivative is cosine of x. I guess I should put a question mark here because we're verifying, right? Is y double prime plus y equal to 0? And sure enough, yep, it's equal to 0. So definitely cosine of x is a solution to this differential equation. Now let's check for sine of x. All right, so now sine of x is my f2, taking first derivative of sine is cosine, and then second derivative of cosine would be negative sine, and then again, plugging these into the differential equation, does sine satisfy that the second derivative of sine plus sine is equal to 0? And we got the second derivative was negative sine of x. First derivative is, or not first derivative, y was just sine of x. And sure enough, that's 0. So both of these are solutions to the differential equation. Verify that these guys are, independent solutions. Okay, so we've checked that they're solutions. Now we need to check if they're independent. All right, how do we check that it's independent? Well, they're functions. We did a little nice thing last chapter with the Wronskian. All right, so what's the Wronskian? It was the determinant of, you list each of the functions on each of the columns, cosine of x and sine of x, and then you take their derivatives. Derivative of cosine is negative sine. Derivative of sine is cosine. And we take the determinant, right? We find the determinant of this. All right, so multiplying down the diagonals, cosine times cosine is cosine squared minus, down the other diagonal is a negative sine squared. So you get cosine squared plus sine squared, and that's that Pythagorean identity that it's equal to 1. So this determinant is always equal to 1, which is not 0. And so if you remember, our conclusion is since the Wronskian was not 0, and that's for all x, there's not a single x that it'll equal 0, because it's always equal to 1, then we know f1 and f2 are linearly independent. All right, so we verified they are both linearly independent solutions to this differential equation. Part B of this example now wants us to find, what do they want us to find? Find the general solution. the general solution to the differential equation. Okay, so the general homogeneous solution, right, is equal to just a linear combination of each of your functions, where these guys are n independent homogeneous solutions to this guy. So, all right, so I'll write a little more explanation, but since the order of the differential equation is 2, how did I know that? Because it was y double prime. It's whatever the highest, the order is going to be whatever the highest derivative is. And so it was the second derivative was the highest one. So the order of the differential equation is 2. And F1 and F2 are 2 linearly independent solutions. Well, then they form a basis. For the solution space. So what does that mean? Your general solution is just y equals some constant times the first function plus some other constant times the second function. It's a linear combination of these two functions. There's your general solution. Okay. Then part C wants us to find a particular solution, and they give us some initial values, some particular values. I guess they're not the initial ones, but they give us some. If they want you to find the particular solution, then they'll give you some values. So now they want you to find the particular solution with, they tell us y of pi is equal to 0, and the first derivative evaluated at pi is -2. Okay, so these are the two values we were given. So we start with the general solution here. My general solution that I came up with on the last part was y equals c1 times cosine of x plus c2 times sine of x. So what we're doing now is we're trying to solve for c1 and c2. That's what the particular solution will be, is we'll have numbers here. All right, so what they gave me to find that is y of pi. So y of pi is equal to 0 means plugging in a 0 here and a pi into my x. Now, all right, well, we know those values. Cosine of pi is -1. Sine of pi is 0. And so your C1 is 0. I solved for one of them. Now, they also gave me y prime of pi is equal to -2. Well, but I don't have y prime, so I got to find y prime. Yeah. So what will y prime be? Taking the derivative of this guy. So constant times cosine, derivative of cosine is negative sine, so it'll be a -c1 times sine of x. Derivative of sine would be cosine times c2, so plus c2 times cosine of x. So there's your first derivative. And we are going to plug in this specific value they gave us. So y prime of pi was equal to -2. Means I'm plugging a -2 into the y prime, and I'm plugging in pi to x. All right, so I got a -2 is equal to negative C1 times 0 plus C2 times negative 1. All right, well, that wipes out. Negative C2 is equal to negative 2, so C2 is positive 2. Okay, so that means my particular solution for the values they gave me is going to be y equals, my general solution was C1 times cosine, but C1 was 0. Oh, that wipes out. I guess I'll write it. Okay, so 0 times cosine of x plus C2 times sine of x. But of course, 0 times cosine is 0. So my particular solution will be 2 times sine of x. Pretty straightforward, I think. All right, let's do another example. This one says, given the differential equation, x squared times y double prime, so times the second derivative of y, minus 2x times y prime plus 2y equals 0. All right, so there's a differential equation. We want to verify that y equals x, so f1 of x equals x, and f2 of x equals x squared. And we give this little, this is going to come in a little bit for when x is greater than 0. We're going to verify that these are independent solutions to this differential equation. All right, so let's start with f1. So f1 is x. What's the derivative? 1. Second derivative would be 0. So let's verify it works in this equation. Remember, these are your y's. Yeah, this is, I guess I could do that, right? Y. This is y prime, and this is y double prime. Since f of x is y. And then x squared, that's those a naught of x and a1 of x and, well, yeah, and a2 of x. All right, so plugging them in. So I've got an x squared times y double prime was 0 minus 2x times y prime was 1 plus 2 times y was x. And is that equal to 0 since we're verifying? Well, that's 0, and that's a minus 2x and a plus 2x, and sure enough, yay, definitely a solution. Let's do the same thing with f2. So here's another function that we're seeing, does it satisfy this? So for f2, that's x squared. First derivative would be 2x. Second derivative would be 2. Remember, you're plugging these into y, this one into y prime, and this one into y double prime. Okay, verify if that's true. So we got x squared times 2 minus 2x times 2x plus 2 times x squared. Is that equal to 0? Well, that gives me 2x squared minus 4x squared plus 2x squared, and sure enough, yay, they are. So they're both solutions. They're both solutions to this differential equation, but now we need to check if they're independent. All right, so to check if they're independent, they're functions, so we're going to use the Wronskian again. I'm going to find the determinant of f1 was x, f2 was x squared. Taking the first derivative would give me a 1. First derivative of this guy will give me a 2x. Now, the determinant will be x times 2x, which is 2x squared, minus x squared times 1, and that gives me x squared. Is that not equal to 0? Do you remember how I said that little, when we gave you, okay, when we gave you that this guy, we gave you for x greater than 0. Remember that? So this is definitely for x greater than 0, which is what was given to us. Is x squared ever 0? Definitely not. Not for x greater than 0. And so, since the Wronskian is not 0, then we know that f1 and f2 are linearly independent and they form a basis. All right. So, we verified they're independent solutions. Part B wants us to find the general solution. All right, so to find the general solution, you're just going to write that linear combination of these functions. It's y equals c1 times x plus c2 times x squared. Yeah. The order of the differential equation was 2, and we found these were 2 different linearly independent functions, and so they form a basis, and the general solution is just a linear combination of the 2 functions. All right, then the last part is they're going to give us some specific, oh, that part was annoying, I didn't see that, some specific values and ask us to find the particular equation. So let's find the particular equation. With y1 is equal to 0 and y prime of 1 is equal to 0. All right, so what have we got here? We're starting with this general solution, y equals c1x plus c2x squared. Y of 1 equals 0 means I'm plugging a 0 into y and a 1 into x. Okay, well then that gives me c1 plus c2 is equal to 0. So I can't solve for one of them yet, but I can say c1 is equal to negative c2. I know they're related that way. All right, for y prime of 1 equals 0, you need to find the first derivative. Derivative of c1x would just be c1. Derivative of c2x squared would be a 2c2x. And then plugging in y prime of 1 is equal to 0 means plugging in a 0 into the y prime side and then a 1 into x. All right, so what does that mean? That means that, well, what is that? C1 plus 2c2 is equal to 0. Well, I know this, so if I substitute it in, what, negative c2 plus 2c2 is equal to 0. So that's 0 is equal to c2. All right, so if c2 is equal to 0, that also means c1 is equal to 0 as well. And so what's our particular solution? Well, here was our general solution, but my c1 is 0, times x, and my C2 is 0. And so it's just y equals 0 is the particular solution that satisfies this, well, the differential equation, right, when given these particular values. All right, that's section 1. Nice intro, yeah? Hopefully it was pretty straightforward for you and not too bad. All right, have a good day.